As I was saying, Debbie does determinants. So we'll do these few. Now, one of the things that will be possible, and I sent an email, a clarifying email about this. If you have simultaneous equations, so something like, say x plus y plus z equal to 2 and two other equations, we've actually given you 4 ways of doing this, but 2 of them we might get a little bit confused about. So that's one problem, solving simultaneous equations like this. And 2 things that we've seen is Gauss elimination and Gauss-Jordan elimination. Okay? And in another context, when you're looking for the inverse of a matrix, say whatever, 1, 0, 8, 2, 5, 3, 6, 7, 4, something like this, calculating these inverses, we also do something called Gauss-Jordan. Now, you shouldn't really get confused between this question and this question. And actually, what I'm kind of thinking, and I've said it, if I ask you to solve a simultaneous set of simultaneous equations with Gauss-Jordan, and you just do Gauss elimination, that's fine. It's perfectly okay, because you do the end of the Gauss-Jordan at the end of the question in another way anyway. And doing these, well, these have to do full, this is a totally different question. I have sent an email clarifying this difference. Okay. So we'll fire away here and see where we got. Gauss elimination, term the solution set. Okay. So what we need to do here is, first of all, put this in augmented form. So we have 1x, 3y equal to 4, 4x, 12y equal to 17. And what we're trying to do is we're trying to get it into the form 1, 0, 1. And once we've done that, we can go off and find the solutions. Now, this question, it is more of an exercise. All we're doing is testing you. Do you know when you're doing Gauss elimination if there are no solutions? Do you know how to handle parameters? And do you know how to handle a unique solution? If you're solving any of these normally, well actually if you're solving, I think this one normally you'd use other methods, but actually for these 2, this is a good way of doing it. But it doesn't really matter in terms of the question. It says use Gauss elimination, you have to do it like this. So we have the 1. What I want to do next is turn this 4 into a 0. How am I going to do that?
Minus 1. Minus 4 or 1.
Spot on. So you're going to do 4 minus 4 times 1, that will turn into 0. So you do row 2 minus 4 times row 1. And I get now, so row 1 is fine. 1, 3, 4. And we get 4 minus 4 times 1 is equal to 4 minus 4 is 0. 12 minus 4 times 3 is equal to 12 minus 12 is 0. And 17 minus 4 times 4 is 17 minus 16, which is 1. So you have the 1, you have the 0. Now you want to make a 1 and you can't, so you're finished. What's the conclusion here?
No solutions.
No solutions, because you have 0x plus 0y equal 1. That's impossible. So your answer is no solutions. Done. And that can happen in any simultaneous equations. You can have no solutions. Okay, done. Look at the second one. So this time we have 1x, 2y equal to 3, and 2x is 4y equal to 6. Now, some people will be able to look ahead and see what happens. Does anyone notice anything here?
3 and 6.
Twice.
Yeah, it's the same, actually the same equation. And what that means is you've actually only one equation and 2 unknowns. And in that scenario, you're going to have infinitely many solutions, because there's loads of values x and y that satisfy that. For example, x equal to 0, y equal to 3 over 2. Y equal to 0, x equal to 3. There's an infinite number of solutions. But that'll come out in the wash. We don't have to know that if you don't see that. We're going to go for the 1, 0. We have the 1. How do I turn that 2 into a 0?
Minus 2.
Spot on. Row 2 minus twice row 1. So first row is fine. 1, 2, 3. 2 minus twice 1 is equal to 2 minus 2 is 0. 4 minus twice 2 is equal to 4 minus 4 is 0. And 6 minus twice 3 is equal to 6 minus 6, which is 0. Now we have 1, 0, and we can't get a 1, so we're finished Gauss elimination. Are there solutions?
Yeah.
Yeah. Now what you do is, now usually when there's unique solutions, you're just going to fire away. But when you see this, you have to say, you have to look at the pivots. Now the x column has a pivot, so that's not a parameter. But this here is a pivotless column. This is going to be a parameter. Y can be any value at all.
So if you have more variables than pivots, does that mean so that it's always going to be an integer number?
This can happen as well.
Okay.
Because you have two variables and one pivot and no solutions. So either can happen. It's never going to be a unique solution. Yeah. But just kind of let it happen actually.
If you had top line of the A, right? You had 1 and you'd 1 underneath 3. No? Yeah. That means you'd have solutions.
You'd have a unique solution, yeah. Because you'd have 1 y is equal to 1, y would be equal to 1.
Yeah.
We'll see that in the third one. Okay, so you've got pivotless.
But that's 0 as a parameter as well, obviously, underneath 3. Yeah?
No.
Why isn't it a parameter?
Well, this has no solutions because this has 0x plus 0y.
So there's no parameter but there's no solution.
Well, if there's a parameter, you have solutions. So the way you want to think about it is, you do the Gauss elimination, and really you ask yourself, are there solutions?
But isn't that 0? It's not a pivot, like, so if it's not a pivot, it has to be a parameter.
No, it doesn't.
Why didn't that?
It'd be like this. So you finish and you'd answer like this. You'd say, solutions. Okay. If yes, you look at pivots. Yes, the next question is parameters, yes or no. No. No solutions. Stop. There's no solutions.
Is,
It's not easy.
is it a parameter so you can't break it down to 1, let's say? Is it a parameter then? Let's say if you had x1, x2 and x3, and on the x3 column on the way down, if you couldn't break the last one down, would it be an actual parameter there where you'd have to actually change the x3 to t?
It's complicating it.
Right.
It's as simple as this. Have you got solutions, yes or no? Whenever you have this, you have no solutions. If you don't have that, you have solutions. Always. And you get down to here and you look at the pivots. If there's a pivot that not a parameter, or doesn't have to be a parameter. If you have a pivotless column, that's a parameter. That's what it is.
Right.
Yeah. So in this one, you have a pivotless column, and that implies that that variable, the y variable, can be anything.
Just because you don't have a 1 there, maybe, isn't it?
Yeah.
Yeah.
But it's from the theory. You actually you can mess this around and you can make x a parameter as well. But this is the best way of doing it. Okay.
JP, when you say parameter, how do you...
That means that y can be anything. Can be
Is
any
that your
value.
answer there then, JP? Y is equal to t?
Y can be anything. Yeah.
So when you have a parameter, it means it can't be anything, is it?
Say that again.
If you have a parameter, it can only be one certain thing. Then
No. The parameter is when it can be anything.
Right.
So, for example, here, if you write down this, if you write these equations again, right? You've got x plus 2y equal to 3. Now, this isn't an equation. This is just 0 is equal to 0. That second row is nothing. Now, if you can pick y to be anything, and you can find the x that solves this.
Okay.
So, you can y to be anything. I mean, we use t. It's just that you can pick any number you want. I mean, you can pick 42. And there will be a value of x that solves this. So a parameter is a value that can take is a variable that can take any value at all. Now the other variable, it'll depend on what that is. So y can be anything, but then x will depend on y, as we'll see here in a second.
So is your answer x plus 2t equals 3?
That's going to be and then we're going to solve that. Yeah. So the pivotless column y is a parameter, and now look at the top row. This reads x plus twice y is equal to 3. And now you can actually just leave the y as a y, but it's easier to use this t. So this reads
Wait, just to distinguish that it was it?
It's just because we can do it all the time. And we get x plus 2. So now I'm saying y, we're calling t equal to 3. And we're trying to find x, so take away the 2t. X is equal to 3 minus 2t. So if you want to write down an answer, you could say xy is equal to x is 3 minus twice t, and y is t. And now I can write it like this, t in or. That just means t is any number at all. And I'll go back and show this. Oh yeah. So if you take any, t can be any value, like you can pick whatever you want. I'll keep it as t here, but if you look at the equation that you have, now this is the same equations, so you've only really got one equation, x plus 2y. If you look at x plus 2y, you get x, we're saying, is 3 minus twice 2t, excuse me, minus twice t, plus twice y is equal to 2. It doesn't actually matter what t is. For every possible value t, this is going to be 3 minus 2t plus 2t. This is going to equal 0. You're going to get 3. So no matter what the value of t is, this is going to work. So you have infinitely many solutions.
You've written it out to JP with the 3 minus 2t, comma t. Would you just put
This
that
is fine.
comma, no, the one below it, yeah, that comma t there, did you just put that in then? Or?
Well, it's like x and y. It's just a way of writing. I mean, you leave it there. You're fine.
All right.
And we'll look at the last one. So the last one is 1x plus 3y equal to 2, 4x plus 18y equal to 60. And again, we're trying to go for the 1, 0, 1 pattern. So I have the 1 here, that's fine. How am I going to turn that 4 into a 0? Spot on. So I have, whoa, that line needn't be there. 4 minus 4 times 1 is 4 minus 4 is 0. 18 minus 4 times 3 is 18 minus 12 is 6. And 16 minus 4 times 2 is 16 minus 8 is 8. Now if you want, you can jump off here, but we've been trying to get the 1, 0, 1. So I'm going to turn that 6 into a 1. How am I going to do that? Right, 6, yeah. There's actually pretty much no other option there. You could say multiplying by 1/6, but that's the same thing. You can't use row 1, because if you use row 1, this 0 is going to get messed around. And you can't take away 5, that isn't a row operation. So you end up with first row is fine. 1, 3, 2. 0, 6 divided by 6 is 1, 8 divided by 6 is 4/3. Are there solutions? Are there parameters? No. Because you have 2 pivots. Maybe I'll just draw this here. When you have pivots, so x is not a parameter, y is not a parameter. They can't take any all values. They have to be specific values. So you have a unique solution here. So what you have is the second one here.
B, it's an infinite number of solutions there.
The B, yeah. Because each value of t, there's infinitely many values of t. Each different one gives you a different solution.
So I suppose, in the example supposed right now with your equation there, your infinite solutions is your kind of description of your solutions.
All of them, yeah. Because you can't just say pick one of them.
Yeah.
It's asked for all of them.
Yeah, so what we say infinite solutions,
No, you need
you
this.
actually do up that.
You need that.
Okay.
Yeah, you definitely need that. Okay, so this second row here is reading 1y is equal to 4/3. And this second one reads x plus 3 times y is equal to 2. That's the first row. And because there's 2 pivots, neither of them are parameters, so you're going to get a unique solution. Put in y equal to 4/3. And you can go a bit faster on this if you want. I'll go fairly
Yeah.
steady here, but you can go a bit faster. I mean, that's obviously if you get the right answer, I don't care how fast you go. 3 by 4 over 3, now that's going to be 4. X plus 4 equal to 2. Take away 4 from both sides. X equal to minus 2. So you end up with a unique solution. X equal to minus 2. Y equal to 4/3.
JP, could you not just
Active tree.
calculate there just R1 minus 3 times R2 to make
Yeah.
that a 0 as well?
If you want, and this is called Gauss elimination. Gauss-Jordan is you keep going. You don't have to do it. I'm saying no matter what, you don't have to do it, because if you just do Gauss elimination, I'm going to give you the full marks. I can't remember exactly if the summer paper says Gauss-Jordan, but if you do Gauss, I'm happy enough. You still get the solution. It's, as far as I'm concerned, it's an extra amount of work that you don't need. Because if you look at it, okay, so you're saying turn that into a 0. You actually do it here. You do it here. You take away 3 times row 2. So there's no need. There's none. So you got one with no solutions, no with infinitely many solutions, and one with a unique solution. So what I was talking about earlier in the Gauss-Jordan, you keep going. Now I can just, for a little bit, I can give you a tiny bit of intuition. Now hopefully it doesn't confuse it. It's meant to help, but I'm just explaining what's going on here. With all of these equations, you can write them all in the form y equal to mx plus c. So they're all lines. And what's happening in part A, you've got 2 lines that aren't intersecting. Actually, let me slow down a little bit there. So what I'm saying is geometrically, the solutions of that, say the first equation, if you plot it, it's a line. And the solutions of the second is also a line. And if you're looking for a point that solves both equations, you're looking for a point on both lines. So solving the simultaneous equations is finding the intersection. On the first one, you have no solution, so that means there's no intersection. That means the 2 lines are parallel. In the second one, what's actually happening, you have the 2 equations, but they're actually the same. And geometrically, you have 2 lines, but actually you don't. They're the same line twice. So if you look at a line, it intersects itself infinitely many times. Every single point is an intersection. So you've got 0 intersections, 0 solutions, infinitely many intersections, infinitely many solutions. And then the final one, you have a unique intersection, you have a unique solution, a unique intersection. They're not parallel, they're not the same line, they're otherwise. One solution. So that's what's going on there.
Should ever be asked that?
No. Just trying to give a bit of understanding here what's going on. What else can we say about this? Now, in terms of we'll stay in test mode. I won't blather on anymore. Any questions about this?
No.
Okay, move on to the next. Okay, so this is another potential kind of a question where we basically, there's a problem somewhere else, simultaneous equations somewhere else. It's been put in augmented form and the Gauss elimination has already been done, and you get down to here. I suppose this is not a real problem, this is a pure test problem. Basically we're testing you on, once you've done the Gauss elimination, do you know what you're doing after that? So, so you've got, if you look at it, 1, 0, 0, 1, 0. You can't make a 1, so the next one is 1. This is in reduced form, and in fairness, the question says that. First point is, are there solutions? Yeah, you're right, but on a simpler level at the start, just now, are there solutions? Yeah. It's weird, you asked if are there no solutions. That's not no solution, so there are solutions. Now you go off and look at parameters. So pivots, if this is x1, that is a pivot. This is x2, that's a pivot. There's no pivot for x3, x4 is a pivot as well. So you've got a pivotless column here. That is going to be your parameter. And we'll just kind of label them above. This would have came from x1, x2, x3, x4. Now, you can't do this analysis until you are in reduced form, as this is. So don't you kind of do it halfway through the question. Get your 1, 0, 0, 1, 0, 1, and then do it. So here, what you can say is x3 can be anything. So let's say x3 is t. Now, go from the bottom, work your way up. What does the third row, the last equation, say? Z. These are all fair comments. It's supposed to be x1, x2, x3, x4. Z. I know I meant the last one. If you are, no, it's fine. You would have been okay. If you did say that was Z, and that was x, and that was y, what would you pick that one?
W.
Fair enough. No problem. If you did, I mean, you can name them. It doesn't matter. Yeah. So if you said Z is equal to 8 and W is equal to, no problem. Okay.